Hey guys, welcome back. We're going to continue looking at our data from the 2004 Olympic women's heptathlon. If you remember, Carolina Kloof, she was the one who took gold for that event, and one of the more important scores she got was from the long jump. So we're going to look at specifically just the data from the long jump for those 26 athletes in the 2004 Olympic heptathlon. Alright, so looking at the long jump information, so we're actually on the assignment, on the front page of the assignment, so we're going to go through all those questions. We'll do the whole front page together, so we're just going to get right into it. I think instead of lecturing on it, if I kind of just show you the examples as we go, I think it helps tie it all together. So we're going to input into our calculator the long jump distances for the 26 female athletes. So I'm going to pull up my calculator. I think there's still a few of you guys who haven't picked up your calculator yet. If you will just message me through Remind, a time that works for you, I'll make it work. Alright, so anyway, we're going to go to Stat and then Edit, and then I put it all in List 3. It might take you a while to put all this data in. If you want, you can probably just go off of what I have and you don't have to put it in. As long as you know how to put it in for the quiz and for the rest of the homework problems, it's totally fine. Okay, so I've got it in List 3 there. List 1 and List 2 are the list that I was using for other ones, so I'm just going to keep using the list just in case. I'm going to keep those old lists just in case you guys need something. Like for tutoring. Alright, so long jump links, we're going to go ahead and graph this out in a histogram. So I'm going to go to seconds, y equals, which is our stat plot. I'm going to make sure I only have one of them on. So I'm going to hit 4 to turn the plots off, and I'm going to go back. So second, y equals, stat plot 1. I'm going to turn it on. We're going to go to a histogram, and I'm going to do list 3. If yours was list 2 or something, you just hit second and 3. That'll pull up list 3. And then zoom 9. Is going to do zoom stat, which will fit it for the histogram. Okay, so there's our histogram on here. Now the default window is always going to be pretty funky when you use zoom stat, so we're going to fix it as something that's easier to work with. Namely, we're going to change this, if we look at our histogram over here, from 5.7 to 9.6. So we're going to do our maximum, or sorry, 6.9. Did I tell you guys I have dyslexia? So go figure, math teacher who flips numbers all the time. It's okay. Alright, and then our X scale is easier if we just go by 0.15, and then we're going to hit graph. And if you notice, that graph actually changed quite a bit. Originally it looked pretty skewed to the right, where a lot of the stuff was bundled up on the left. But now it actually looks more symmetrical. If we look over here on the side, this value looks like it's a potential outlier. And we can actually test to see if it's an outlier pretty quick by just simply putting a modified box plot right above it. So for plot 2, I'm going to turn that one on. Now, if you remember and use the fourth option, we don't use just normal box and whisker plots. We always use the modified ones because we want to test for outliers. Normally, we can test for outliers by doing the interquartile range times 1.5, add it to list 3, subtract from list 1, all that good stuff. Alright, then I'm going to hit graph again, and sure enough, this will tell us at that point, which was Carolina Kloof's, her long jump distance was considered an outlier, and more or less from the box plot you can tell it's unimodal and symmetric, but even better than that, we can look at the histogram and we can tell from there. Alright, so what we want to do now is fill in that data. So how many do we have from 5.7 to 5.85 but not including it? So that's going to be 1, 2. So we fill up to 2, and notice it is going by 2 over here. Just for your viewing pleasure, I've already pre-populated that out. So that looks like 2, 4, and then we had 5, 8, back to 5, 1, and 1. Anyway, another important information is we want to go ahead and find the one variable statistics for that. So to do that, we're going to go to Stat and arrow over to Calculate. One variable stats, list 3. You can leave the frequency list the same, then calculate. So we have a mean of 6.16. That's going to be really important now because we're going to be using normal curves or bell curves for it. And the standard deviation of 0.23, I just rounded. And you can find your 5-number summary. We're not really going to use that information anymore because our distribution is unimodal and symmetric, so we'll just use the mean and standard deviation. But if we had anything else except unimodal and symmetric, if it was bimodal or if it was skewed, we would be using interquartile range and median, right? Okay, so that's pretty much what we need to know from this one. Next thing is, does it seem appropriate to you to model distribution with a normal model? Well, that's what we were just talking about. Does it look like it is unimodal and symmetric? I would say yes. Now, do we have outliers? Yes, we do, but I think this outlier is going to be okay. I don't think it's going to be an issue. It's not like really far out there. and it's also it's going to be kind of balanced off by what we have going on over here, because it is really kind of slightly skewed to the right, but I think it'll be okay. The other thing is you need to keep in mind is that this is just a model. The normal model is just that. It's a model where the actual distribution, the histogram, green and green, see that? That's the actual data. So the data is never going to fit perfectly with the model, but as long as it's close and it's unimodal and roughly unimodal and symmetric, we're good to go. If it was heavily skewed or if it had crazy outliers or outliers in general, then we wouldn't be able to do it. Alright, calculate the percent of observations that fall within 1, 2, and 3 standard deviations. So this is our empirical rule that we learned on Friday. So for a normal model, we have 68% of all the data would fall within 1 standard deviation, which goes to the inflection points, right? 95% of the data will fall within 2 standard deviations for the model, and 99.7% of the data would fall within 3 standard deviations. Go into there. Now we go ahead and we can calculate those 1, 2, and 3 standard deviations by using our calculator. So we had a mean of 6.16 with a standard deviation of 0.23. So we're going to do 6.16 plus 0.23, then hit enter, then do plus 0.23 again, and then hit enter, and then enter again. And that's going to be adding 3 standard deviations to it. And then to go backwards, we're just going to do the previous answer minus 0.23, and then that will take us back to our mean, and then just do it 3 more times, and that'll take it back. Okay, so that is the easiest way to be able to calculate what your points are here. So notice the 5.47, 5.7, 5.93, 6.16, and then those other ones we would scroll up for. Okay, so that is the easiest way to do it. You will need to know how to do that for the quiz and for the test. Sorry, we already took our quiz, so it would be our test, which will be in about 2 weeks. We're testing the 30th, yeah, so it'll be right before, anyway, 2 weeks. Alright, next thing. So we have our bounds here. So for within 1 standard deviation, that's going to be from 5.93 to 6.39. What number of athletes fell within that? So we're going to go back to our data, or I guess I can pull that up on the calculator here. So stat, edit, and we're going to go, our lower bound is 5.93. So this is the first one. So we have 1, 2, 3, 4, 5, 6, 7. Okay, so there were 19 altogether. There is an easier way to do that. So what we can do is find the one that would be just within the top, which is from list 3. It's the 23rd term here. And then we can go back to the one that's right below it, or the first one that would be within it, which is here, which is the 5th. So we can do 23 minus 5, and that will tell us how many are going to be between it, which we said was 18, I believe. Alright, so the number we had was 18. I'm going to hit second quit to quit out of that. And I'm going to do 18 divided by 26, because there were 18 out of 26 of the athletes that were within 1 standard deviation, which is going to be 69%. So here I'm just going to type 0.69, or you can do as a percentage. Either way, it does the same thing. Alright, oh, sorry, actually that's in the wrong place. So this is going to be, we said 18, and the percent was 0.69, or 69%. I guess it was already labeled as percent, so I'll just do 69. Alright, what would the percent be if we were talking about a normal model? And well, in the model it would be 68, but our actual data from the distribution was 69. So that's actually really close. And this is the actual data. I didn't mess with it or anything, which is kind of cool. Alright, what about within 2 standard deviations? So that's going to be from 5.7 to 6.62. What number do we have on that? So I'm going to do our little trick here. So I'm going to go stat, edit. I'm going to start at the very top and find the first one that would be within that bounds, which would be this one right here. So it looks like there's only one that's not going to be on the upper bound, and here on the lower bounds, all of them would be, because 5.7 was the lower bound. So there's only one that's not going to be, so that's going to be 25. So that's not too bad. And the percentage would be 25 out of 26. So let me quit out to the main screen. So 25 divided by 26, which is going to be 96%. So I'm just going to label that 96. And in our distribution, it should be 95%, that are within 2 standard deviations. At least that's what the model would say. And that's, again, really, really close. And 3 standard deviations, I'm pretty sure everyone is within that, even our outlier. Okay, calc edit, which the highest one we had 6.78. And yeah, 6.85 was the highest. So all of them are going to be that. So that's going to be all 26 of them, which would be 100%. And from the empirical rule, we would say it should be 99.7. So notice how well does it fit. So just compare these two, the actual data from the model from our histogram and the data that we would get if we used our normal model. Those are really, really close. So it shows us that our normal model is really appropriate for us to use, but we actually knew that because it was unimodal symmetric. But these will match up pretty closely if the data is unimodal and symmetric. So instead of having to use the actual data and look at all the percentiles on that, we can just use the model, which is going to be a lot easier to work with. So there's actually many distributions that follow a bell curve, and kind of the general rule is anytime we take repeated measurements of the same thing over and over and over again, like in manufacturing, if we're manufacturing a basketball, right? So the basketballs are all going to be about the same width or have about the same diameter, but there's going to be some variability in the system in the manufacturing, and so the average diameter of the basketball is going to be pretty consistent. That would be whatever would be the most common one would be the average. But then there is going to be a certain standard deviation where you're going to have some variation where some of the balls are going to be larger and some of them are going to be slightly smaller as well. And we'd expect that to follow along a distribution of a normal model. Also, so here's another example. So male full-term birth weights. So full-term birth weights for males is about 7.6 pounds. It might actually be 7 pounds 6 ounces. I think it's actually 7 pounds 6 ounces, but I did 7.6 to make the math easier. My bad. And then for females, it's 7.2, or not 7.2, 7 pounds 2 ounces. See, this whole like pounds, ounces thing, kilos would be a lot easier to work with. But anyway, so we're just going to say it's 7.6 pounds with a standard deviation of 1.3. Another one is the ACT score. So nationally, the ACT has an average of 20 with a standard deviation of 5. Some years it changes, but that's generally what it is. Now in 2017, the last time that we had data from Putnam City High School where all the juniors took the ACT, we as a junior class had an average of 17.6, which is well below the national average, might I add, and a standard deviation of 4.2. So we were more consistent than the national, but we were also definitely below the national average. So those would fall under a bell curve. IQ scores also fall under a bell curve. Average weights will fall under, or average heights will. Weights will not, because you can always, it's going to be skewed to the right because you can always be bigger. At some point you can't really get any smaller. But there are many things. The width or the diameter of your head, that's going to also follow a bell curve. Many things will. We do have to be careful about differences in male and female. If we graph male and female heights, it would be bimodal, so you should really separate those into subgroups like we are doing here with birth weights. Only look at the males because they're about 4 ounces on average, 4 ounces heavier, I think, if I remember right. Alright, so cumulative probability function. So we're going to learn how to calculate percentiles. It's in the calculator, which is really good. So let's go ahead and calculate what your percentiles would be. So this is example 2. Alright, so what's the z-score of your birth weight and ACT score? So we'll use my birth weight and my ACT score the first time I took the ACT, which would be kind of comparable to the juniors taking it for the first time. And we're going to see how I would have done, compared to them. So we're looking at the male birth weights. If you're female, you can just do 7.2, and then for all of these, just subtract 0.4 from all of them, and then we'll call that the distribution for females. So my birth weight was 9 pounds 9 ounces. So what I'm going to do to do the 9 ounces, to convert that to just pounds, I'm going to divide 9 by 16, which is where I get this 0.56 thing business going on. So I was 9 pounds, 9.56 pounds. I was a really big baby. Anyway, let's see. So centered at 7.6 with a standard deviation of 1.3, so that goes to the inflection point. 9.56 is going to be about 1.5 standard deviations above the mean. So if we calculate the z-score for that, it's the observation minus the mean, which is basically how far you are deviating from the mean, and then divided by the standard deviation, which is what standardizes the scores to allow us to compare wider spread distributions to more narrow. And I'm actually exactly 1.5 standard deviations above the mean. So the next thing we want to do is find out what's that percentile. So the percentile is going to be what percent of babies were my weight or below my weight. And so what we're looking for is the area. Let me fix that real quick. Control-Shift-H. Alright, so we're looking for the area that is underneath the curve going all the way up to 1.5 standard deviations, or a z-score of 1.5. So we want to know what the area is under the curve. So don't worry, there's no funky calculus going on here. That is all programmed into the calculator, which is really nice. So we need to go to this cumulative probability function. So CDF, cumulative density function. Yeah, this should say density. Anyway, so we want to find the CDF of the area underneath the curve. So we're going to go to second variables, which is the distribution, so the little blue distribution there, and we're going to go to the normal CDF because it's the normal model. We want the cumulative density function, not the PDF, which is the probability density function. So I definitely got to fix that. That should be the cumulative density function. Alright, so normal CDF, the lower bound. Okay, so we want to find the area under the curve. Our lower bound, we could just say 0, right? Because we're not going to have anyone with a birth weight less than 0. But the default that you're going to see on your calculator is going to be negative 999 or 9 times 10 to the 10th power or whatever. Anyway, that's totally fine. It really doesn't matter how far over you go. That will be just fine. Like I said, on this distribution, we could just go to 0 and it would be fine. We could probably even do 3 and it would get all of it. Our upper bound in this case we're going to do is going to be 9.56. The mean is going to be centered at 7.6 for our distribution with a standard deviation of 1.3. Then hit paste and then hit enter. And that's going to tell me the percentile, the area underneath the curve, the cumulative density function from the left bound to the right bound for that specific normal model, which was parameterized by a mean of 7.6 and a standard deviation of 1.3, is going to tell me that I was in the 93rd percentile. So what that means, you can interpret 93.4. Wow, there goes that dyslexia again. Anyway, so what that means is that I was the same weight or heavier than 93.4% of babies, male babies in particular. Okay, so yeah, I was a big baby. Another way that we can do this is actually, so I'm going to go back to second distribution, is by using that z-score. So if we've already calculated the z-score, we can go a lower bound from basically negative infinity to an upper bound of the z-score of 1.5. The mean now for using z-scores is centered at 0 standard deviations with a standard deviation of 1. Okay, so it's centered at 0 with standard deviation of 1, because again we're using z-scores with our, it's kind of a standard normal distribution, but it's whenever it's centered at 0 with 1 standard deviation being 1. Alright, anyway, when you hit paste, you'll notice, whoa, we pretty much get the exact same value, which is nice. The only reason there's any difference here is because it was actually not 9.56, there was decimals that we rounded off, right? You'd like the 0.25, and that's why there's a discrepancy between the two. So anyway, if you have the actual values, you should probably just put it in like that, like we did here with the 0.76 and the actual values. But if you already have a z-score, just use the 0 and the 1 and go from there. So hopefully that makes sense. Let's move on to the next one. So with yours, graph out what your weight is. And again, if you're female, you can just subtract 4 ounces or 0.4 pounds. I know that's wrong, but anyway, you can just do that. If not, you can use that. Alright, so for the ACT scores on this one, so the first time I took the, so you can populate these as well by doing our average and then adding the mean each time, or the standard deviation, and then subtracting the standard deviation like we've already done. We want to know the z-score. So first time I took the ACT, I actually scored a 24. I think I was a junior when I did it, so we're just going to go off of that and compare what that value is. You can use your actual ACT score if you've taken it. I'm pretty sure all of you guys have probably taken it by now. So we're going to do, to find the z-score, anyway, 24 minus the mean divided by the standard deviation, which is actually, believe it or not, really close to 1.5 as well. So as unusual as my birth weight was my ACT score compared to Putnam City High juniors of 2017. Anyway, to find the percentile, we do the same thing we did before. So we're going to do second variables to go to distribution, go down to the normal CDF. We're still going from the left because we're doing percentile. And the upper bound, I could use the 1.52 if I wanted to, but since I have the actual data, I'm just going to use the actual data. Alright, so 24, delete those. The mean was 17.6 with a standard deviation of 4.2. Alright, and then hit paste, it's going to be 93.6. So really close to the last one because their z-score was almost the same as well. Alright, so now we have Tiger Woods. So this is example number 3. So on the driving range, Tiger Woods practices his swing with a particular club by hitting many balls. When Tiger hits his driver, the distance the ball travels follows a normal distribution of 304 yards with a standard deviation of 8 yards. And we know that because the model here, the first one is the mean and the standard deviation is the second. So you can go ahead and fill in those values. We want to know what percent of Tiger's drives travel at least 290 yards. So at least 290 means 200 or more. So if we go from the left and we go to 290, somewhere about right there, that's going to be the percent that are below that range. Now we could calculate that and then subtract it from 1 because all of it's going to add up to 1 if we're dealing with percentiles. But what's easier is actually just to go from the other side. So we want something that looks like this. So how do we get that area under the curve from the calculator? Well, we do the same thing we've been doing. So second variables, normal CDF again. Our lower bound this time is going to be 290. Our upper bound, we're going to do 999. Again, realistically, we could probably go to 350 and it would be big enough, but just get in the habit of putting a bunch of 9s there because the calculator doesn't care. The mean, 304, standard deviation of 8, and then just hit paste. And it looks like 96%, we'll just round, 96% of all of his drives go at least 290 yards. And you can draw a picture and shade that in. It's pretty much what we're doing. What percent of Tiger's drives travel between 305 and 325? So that's going to be the area from like 305 to 325, so you just shade in that region. To find the CDF for that, as you can probably guess, we just go to second variables for distributions, the second one. Our lower bound this time is going to be 305. Try that again. Upper bound in this case is going to be 325. The mean and standard deviation is still the same. And there you go, it calculates it for you. So we'll round that to 44.6% of all of his drives travel between 305 and 325 yards. Alright, so hopefully you guys are kind of catching the drift through the whole thing. Let's look at number 26. IQ. So some IQ tests are standardized to a normal model with a mean of 100 and a standard deviation of 16. Draw the model for use with these IQ scores to the right, or below for me. Clearly label it showing the empirical rule, which is 68, 95, 99.7 as it predicts. Alright, in what interval would you expect the central 95% of IQ scores to be found? So if we look at our model, or our empirical rule here, 95% of all the data would be within 2 standard deviations. So go ahead and fill this in. We're adding 16 each time, subtracting 16 from the other direction, and the middle 2 standard deviations would be anywhere from 68 to 132. So that would be the answer to the first one. And to label the empirical rule, you can just draw the lines extending up, and 68%, 95, 95, just like you saw on the one above it. Alright, part B. In what interval would you expect the central 95%? We just did that. Okay, moving on. Alright, part C. What about what percent of people should have IQ scores above 100 or 116? So that's going to be this up here. Now I filled in these percentages based on the estimate, which is from the empirical rule. So if 68% is within 1 standard deviation, half of 68% is 34. So 34% would be standard deviation above, and 34% is standard deviation below. Now if you do the difference between 95 and 68, that's going to give you 27%. So half of 27% is here, and the other half would be there. So we have 13.6 is going to be between 1 and 2 standard deviations above, and 13.6 or 13.5% is between 2 standard deviations below and 1 standard deviation below. Doing the same thing between these two, so that's going to be 4.7 divided by 2, which is going to be 2.35%. It's going to be between 2 and 3 standard deviations above, and 2.35% is going to be within 2 standard deviations below. So all this breakdown here pretty much all comes from the empirical rule. I just broke it down like that so you can see visually what's going on. So we can find estimates from the empirical rule, or we can plug this in the calculator so you don't actually have to remember that. So what percent of people should have IQ scores above 116? So 116 is here, so it should be 13.5 plus this one. It's actually going to be a little bit left over, which is going to be half of the other part. So there's many ways you could do this. You could also, half of it's going to be above the mean and the other half's going to be below the mean. So you could just add the 34% to the 50%, which should be below it entirely, which would give you 84%. Another way you can do this is by putting in the calculator, which is pretty helpful. So we're doing 2. So our lower bound, we're going to do negative, and I have to make sure I push the button on this one, so negative 999. The upper bound, we're going to do 116. Again, we could probably do a lower bound of 0, but whatever. Centered at 100 with a standard deviation of 16. Hit paste, and boom, so 84.13. So from our estimate from the empirical rule, we would just say 84%, but the actual value, you'd use the calculator. So I'm going to use the calculator on the other ones. What about 68 and 84? 68 and 84, well, that should be about 13.5 if we're using that, but using our model here. Oh yeah, by the way, you can also arrow up and then just change those values. So instead of going from 100, we're going to now go from 68, not 69, sorry, 68, and then our upper bound is going to be 84. All right, then hit enter. So they're saying, what just happened? Let me try that again. Okay, so I did the wrong things. Okay, so our lower bound, you know what, let me not do this because it would be easier if I just do second distribution. Second one. Okay, so our lower bound is going to be 68. Upper bound is going to be 84, centered at 100 with standard deviation 16. I changed the wrong ones. What did I just do? Okay, so I wasn't on the wrong. Okay, so let me try this again because I wasn't on the right thing. I have to be on the bottom line before it let me do it. Good thing it saves it, so it's pretty easy to put it in. Alright, so 13.6%, which we set 13.5 from our estimate. What percent of people should have IQs above 132? Well, again, it's going to be 2.35, but a little bit more for what the part that's beyond that. But again, we're just going to put it in the calculator at this point. And you could subtract the 50% over here plus this part here, which would be 47.5, so that will leave us with 2.5. So there should be 2.5%, but we'll get the value from here. So we're going to go a lower bound 132, upper bound 999, whatever, and should be close to, as we said, about 2.5%. Okay, so apparently it's smaller than that. I'm not sure quite what I did wrong. Oh, it's because these are estimates and they're not exact. Okay, that's fine. Moving on, 28. Next size 26. The purposes of modeling IQ scores proposes modeling with that normal model. What IQ would you consider to be unusually high? So we would consider anything to be an unusual if it's more than 2 standard deviations from the mean. So 2 standard deviations above the mean in this case would be 132. So if you had an IQ of 132 or above, we would consider that to be unusually high. It would be an unusual observation, in other words. Alright, so that is it. If you have any other questions, you can always join me at from 1 to 2 for our Google Meet. But besides that, I'll see you guys later and have a good day.